framework, graph-based generative scheduling in construction project management. And this work is a collaboration between the University of Hong Kong and the Santa Clara University. To summarize our research in one sentence, our research addressed a disconnection between the parametric design and the production planning. We tackle this by proposing this generative framework that leverage the graph rewriting techniques. So I've broken the presentation into the 5 core sections. First, I will introduce you to the motivation behind the work. And next, we will study the existing literature on the production planning and graph-based modeling. And from there, I will present our generative framework. Basically, that includes the graph rewriting and the schedule formulation. Finally, we will I will show you the result using this demonstrative case study. So unlike automotive lines, like modular construction deal with the massive design variability and product heterogeneity. And that means every single module different from the room configurations, wall dimensions, and openings of doors and windows. With our existing scheduling tools, they are quite rigid and static. I will later explain why I argue in this way. When a designer modify a room configuration, the planning of the downstream task and the resources will break down. And this manual effort required to adjust the schedule to adapt this design change is slow and expensive. This is why we need automation. And to solve this scheduling problem, the industry has relied on many scheduling tools. For example, the job shop scheduling is one of them. This research has applied this formulation to precast concrete, the pipe spool fabrication, and steel component manufacturing. And this approach is great at optimizing the make-span resource utilization and the workflow reliability. However, they almost assume that the task structure are predefined and this process logic are also static and predefined. And this means they cannot adapt to the design changes and also not scalable to different module configurations. On the other side of the literature, we see a growing interest in graph-based modeling. Researchers have used this graph to represent special module topology, spatial relationship, and design dependencies we have seen in previous presentation. And in the scheduling world, disjunctive graph are also widely used to represent precedence, constraint, and or resource conflicts. But here is a critical gap. So we see there are two powerful graph domains, they remain completely isolated. So which means the design graph used by the architects, they are not fit into the production managers when they create their schedule or production plan. And our goal is to connect those two isolated worlds, the design and the production, directly into a unified model. And this gap leads us directly to our core research question here. If we are given a customized parametric modular design, how can we automatically generate the correct production tasks and allocate the right resources and map out the exact sequencing constraint to produce an optimized schedule? And here is how this is what we proposed, the generation scheduling framework, how this framework achieves this goal. And this process can be unfolded into 3 steps. First, we take a parametric modular design and represent it as the graphs, undirected graph. And second, we run a rule-based transformation using the graph rewriting engine. And this engine basically matches the process templates from the rule library and append the production logics. And third, we translate this task-enriched graph into the job shop scheduling problem, and we solve the model and generate and output the optimized schedule. And later, let's look at each step in a closer detail. So the step one, the design of a prefabricated modular design is represented as undirected graph. The wall nodes carry the nodes in this graph represent the wall and the rooms. And for example, the wall nodes also carry the geometric property like the length, width, and the number of opening and the door. And the room nodes also capture the width, length, and the area, the floor area, and also the category of the rooms, whether it's a wet room or a dry room. And this edge between the room and the wall nodes represents the physical boundaries and defining like which wall perimeter the which rooms. And in step two, we apply the graph rewriting, which is a formal rule-based approach for modifying the graph structures. So our rewrite rules like work by searching the design graph for a specific pattern, which we call that the left-hand side of the rule. And when a pattern match is found, the graph rewriting engine executes the transformation on the right-hand side. It preserves the original design nodes, but augments the two type of nodes. One is the task node representing the discrete production activities, and another is the resource node representing the factory crews or equipment. It also we also build the edges between the task nodes to represent the logical precedence between these tasks. And to ensure our generative rules are scalable and easy to manage, we structure this rule library into three-tier hierarchy. At the base level, we have the element level rules which handle the task for individual components like the regular walls. And in the middle, you see the room level. Like rules which aggregates like finishing activities and for functional space, and this can be distinguished between the dry room and the wet rooms. At the top, the module level handles the holistic task for the volumetric module unit, and such as the structure framing and the close-out inspections. And this hierarchy structure basically turns like the manufacturing knowledge at different levels into the reusable like process templates. And once our task graph is populated, we formulate the final step as a job shop scheduling. In this model, every custom building module on the order list is regarded as the unique job, and the generated task node becomes the individual operations, and the factory the workstations and crews are modeled as resources, and crucially, the task durations are calculated on the fly, which means like we extract the geometric parameters from the design nodes and multiply them by the predefined productivity rate. We can estimate the task duration, and this ensures that every task duration is consistent with the actual design. And in a traditional factory environment, the workstation are fixed in place and the product moves along the assembly line. However, the volumetric module are quite heavy, and so we treat each of them as a stationary and model the factory crews as the movable resources that navigate between the modules. And we feed our the generated task graph, order demand, and the resource capacity into the solver, and outputs to minimize the overall production timeline, the mix span. To validate our framework, and we built a prototype and tested against a residential module from the fabricator in Asia. And we used the network X and the regraph. Those are Python library for the development. And once the task graph was compliant, we fed it into the Google solver, and we assume the standard factory capacity and to generate the optimized schedules. And here is a very simple prototype, and on this slide, this is the task like defined to produce the module, and the project manager can easily edit the physical dimensions of the module and entering change the size and then height and length, and the application immediately updates the graph in the back end.
1 minute, Ben. 1 minute.
Oh, okay. So. And like the user can simply input their target mark span and the dashboard limited to the scheduling, where links to the scheduling model. And from here, the engine evaluates the parametric design, runs the graph rewriting, and solves the job shop scheduling. And here are some insight when we scale the production from a single module up to 20. Like we see, like there is a nonlinear relationship, which means like once we increase the resource and at the very beginning, due to the efficient parallelized utilization of our resource, the fabrication time per module decrease a lot. But when the shared resources become saturated, we see like this productivity climb again. And then by plotting the stations and the resource saturation rate against the task queue time, we can identify the critical production bottlenecks. Here, like you see, the framing station is a critical bottlenecks, and the installation station is underutilized, which this visibility allows manager to make data-driven decisions about the crew like rebalancing. And this finding also demonstrates the tool proposed by us is not just a scheduling tool, it can also serve for analytic purpose. And so this is like the end of my presentation today. I will show you some like limitations. So the first, like the framework relies on the initial setup phase to build such a robust product process rule library, which requires like close collaboration with the manufacturers. And the second, like our current formulation assumes deterministic task durations, which might not, which need to be adapted to like the dynamic environment, subject to the disruption and learning effects and the workforce variabilities. And those we are going to solve in the future work. And okay, so to conclude, we have presented our graph-based generative framework that can bridge the gap between the architectural modular design and the production planning. And by abstracting, so in this framework can be summarized in one sentence, is to abstracting a modular design as a graph and using the graph rewriting rule to automate the automatically append the process logic and leveraging the constraint programming solver and to generate the schedule automatically and also identify the production bottlenecks. Thank you for your listening, and I'm happy to answer any of your questions.
Okay, thank you very much.